Right. Good afternoon. Uh, so hopefully you had fun with the first project. We ended up with like 3.8, I guess. And it seems that, it's a machine learning based kind of like perceptron based branch predictor, which is a sad day for traditional kind of history based uh, non-machine learners, but machine learning is doing well for a reason, right? So
In modern data center, it's they use state, like state is not machine learning.
it's not machine learning, yeah. I mean, but perceptrons, I know, I think I've heard from some faculty that they're working with AMD, and apparently AMD is using some form of like simple perceptron. But yeah, I think modern processor, we nobody knows exactly what's going on the branch predictor of these modern processors, but the assumption is some form of Tate, yeah, because it's just simple history.
Yeah.
Very simple. Because like when it comes to the actual hardware implementations, things are crazy, right? So you have to just go with something simple. Because like we are doing all the simulations as we might, but implementing these things is a different beast. Yeah.
What is the realistic memory size that these are limited to?
I think the competition you're talking about, like, I think few tens or hundreds of kilobytes is reasonable, I would say. Yeah.
Perceptrons for a reasonable accuracy, if we were doing the comparison, they would need quite a bit of it.
They would be quite what?
They would need quite a bit of it here for reasonable accuracy.
For reasonable accuracy? Yeah, well, it's trade-off. I would say like nowadays hardware is cheap, so you can actually afford to have bigger. I think the only reason for not having bigger is the latency of your that kind of history table also, because this needs to be queried per cycle, right? So if it's like too big, then it defeats the purpose because it's not you cannot really kind of query it as fast as you want. But yeah, these are nice trade-offs in terms of implementation. If some of you might actually join one of some of these computer architecture companies, and you'll see some of this in future. But generally, branch predictors have been like very popular area of research for a very long time. It's not anymore, but I'm sure that it's still hardware companies are doing implementation and all. Anyway, so going back to and then by the way, the second project has been released. This one is about replacement policy, mainly the things that we discussed last time. So make sure to watch the lecture and start early. Now you know that it takes some time. But basically the kind of format and the topic is like everything is very similar. The framework is obviously different. It's actually this one is even simpler than the branch predictor. It's just very simple timing based kind of like simulator. It's already LRU, I think, and RIP is provided. My guess is that most of you are gonna do some form of drip or dip or some form of dynamic based replacement policies, but be my guest and do machine learning or other things as well. See if Perceptron would be helpful in this. But yeah, if you have questions, feel free to ask. Another big thing is that starting next week, we are doing our presentations, right? So, I mean, the class size and names and all is changing a lot. So there might be like people who are signed up and then they drop the class. There might be people that will sign up and their names are not in the list. So please, everyone, we're watching, we're in the class or watching the lectures. The first thing you need to do, go to the website, check the schedule, see if your name is there or not. And if it's not, immediately contact me and then I'll add you somewhere, okay? And it's very likely starting next week that we see some papers are assigned to some people and they've dropped the class. So we have to kind of skip those papers. So let's see what happens next week, okay? All right, so now going back to what we were last thing that we were discussing, a few slides remaining from this part. I need to finish this. So if you remember, we were talking about cache and partitioning between multiple different cores. The reason for that was like, cores might demand more cache space, but we cannot just give it to them because some of these applications may not use cache properly. So we may need to have a more strategic and more intelligent way of partitioning, where essentially we kind of like foresee who is going to use and benefit more from the cache and provide that to that particular application, rather than just kind of saying that, okay, it's free for all, whoever wants it, we're going to do it. And then the idea that we introduced was this utility-based cache partitioning, which essentially we show that there are kind of three types of applications. There are those that are low utility, high utility, and kind of like somewhere in between, that they're high utility at the beginning and then low utility after a while. So we need to kind of like measure this utility and then do proper action for that utility. How do we do that? We use a monitoring logic. We call it UMON. And then this monitoring then feeds in their kind of sensing data into some partitioning algorithm. And the partitioning algorithm is kind of implemented and enforce the partitioning in the cache. For example, if you have like, L1 caches that are private and L2 cache that is public, sorry, not public, shared, then we want to have this partitioning algorithm for this shared cache, okay? So how do we do that? We're gonna use this idea that's very similar to this auxiliary kind of like tag domain that we had for dip and drip and so on and so forth. We're gonna have this thing called auxiliary tag directory, and then gonna have counters for each of these tag directories. So think about this, that we have this set of, different group of sets. And what we have is we're gonna have counters per weight in this cache, okay? So for example, if this is a 16 way, then we're gonna have one counter per weight, okay? And then what we're gonna do is that we're gonna count this the amount of hits in each of these ways. And the way that we're gonna do this is we're gonna first assume that, if this application had only this just one way, how many hits this would have been had. Then we're gonna think about it has 2 ways and 3 ways and 4 ways and 5 ways and so on and so forth, and then use this counter to count that. And then essentially this way we can say that hits in 2 ways is essentially the counter H0 and H1, because this is all the hits that you get in way 0 and all the hits that you get in way 1, right? And then you can actually repeat this for all the applications. So that's what it's essentially, you can have one of these auxiliary tags per application. So for the same sets, you have multiple of these auxiliary tags. Each one has their own counters. And this way you only kind of limit them to number of ways. So saying that, okay, if it was only way 1, or it was way 1 and way 2, and then way 1, way 2, and way 3, and so on, how does this change the hit, okay? Then what you will see is that, you see numbers for different ways. And this way you can plot something like this, right? So you can actually see the number of hits, or in other words, the miss rates. And then you can easily plot some figure like this. Essentially, you just need to monitor these counters, okay? In order to make this reasonable, we cannot do this for every single set. So what do? We use the same trick that we used many, many times in this lecture, and that's gonna use dynamic set sampling. We're gonna just choose a subset of the sets that we want, and then apply this kind of auxiliary tag and this kind of monitoring for only those subset, okay? Then what we'll do is we're gonna essentially now just need to decide how to partition. So we have these counters, right? So we have H0 all the way to H15 for application number 1, and then we have the same for application number 2. For now, let's assume that we have only 2 applications, the simplest scenario, okay? So we have hit score for application 1 and hit score for application 2, okay? So this is for the monitoring 1 and monitoring 2. So now the question is, how should I divide this cache between these 2 applications? Essentially, the way I need to divide is this kind of like where these 2 numbers should be divided, right? And what do we want to divide is we want to maximize the hit score 1 plus hit score 2, right? So essentially, for example, let's say that the division would say 15 to one core and 1 to the other core, which means that I'm basically going to do H0 plus H0 from this one all the way to H16, 1 minus 1, which is H14, okay? In other words, there is one application that really benefits from having more cache, and the other one that has nothing gets nothing useful from the cache. Okay, this is kind of the most extreme way of thinking about this. Probably in more realistic scenarios, this number would be kind of maybe half or somewhere close to half, right? So essentially, the idea is from this, all I need to do is finding the right cut point such that these two numbers are the maximums. How do we do that? For 2, it's very simple. All we need to do is really kind of looking at all the possibilities, right? So we do 1 and 15, and we measure the score. We do 2 and 14, all the way to 15 and 1, right? So 15 different possibilities, and then we know the answer. Okay, very simple kind of solution. The problem, though, is that if you go beyond 2, go to 3 or 4 or 5, this becomes a very tough problem because now you need to do all the possibilities, and then possibilities exponentially grows, right? So what should we do then? Well, the original author of this idea shows that this essentially becomes an optimization problem. You can do things like really search, for example. So you can do like, you can start with some assumptions and then do some small optimizations in order to find the optimal answer. Of course, it's not guaranteed that you can always find the answer because this becomes kind of like an NP and NPR problem. But what you can do is at least you can find some level of optimum solution for this. Okay, and then what you can do is that since this is a dynamic partitioning, you can dynamically repartition this at every X million cycles. So for example, they originally suggested that it would be a good idea to kind of repartition every 5 million. The reason for doing it every 5 million is we're anticipating that after a few million instructions, the behavior changes. Okay, so it's a good idea to not just statically kind of partition the cache. Instead, looking at this monitors and every once in a while, try to optimize the new numbers and then repeat this process over and over. Okay, so essentially, this is kind of like what we're gonna get. So we're going to have this way partitioning algorithm that takes this two numbers, this way given number. So this is the number that we are getting from here. So for example, 15 and 1. So one cache should get 15 ways, the other cache should get 1 way. So what we should do is we check whether we have enough ways applied to one application, and whether there is enough ways applied to one application or not. If not, then we allow the application to kind of occupy more ways. If it already kind of occupies the maximum amount of ways, then we don't let it to grow, right? So we kind of like minimize the amount of growth of that application. So for example, if we have a cache like this, that this portion is for one application and this portion for the other application, if a miss from this application comes, we're going to basically pick things from this only smaller portion. And if we want to replace anything, we're going to replace it in here. We're not going to kick anything out of here and replace it here. Okay. Same thing for the red. So if something comes here, we're going to replace it with something here. So essentially, we're partitioning this cache into these two different parts. Okay. And then if there are multiple of them, then we are obviously partitioning into multiple of these. Okay. So essentially the idea is three steps, right? So 1 is monitoring, then 2 is kind of like deciding the partition, and then 3 is enforcing the partitions, right? So this is kind of like the idea of this monitoring. And then you can repeat this over and over again if you need to. Okay. And as I said, what should we do if beyond two, there are, greedy algorithms that one needs to do and so on and so forth. Another way of thinking about these kind of partitionings is what we call cache coloring. So for example, instead of like, partitioning the ways, one can kind of color the rows, the sets, and say that, okay, this group of sets belong to one application, this other group of sets belongs to another application, and so on and so forth. In other words, we color each set, we mapped each set into different addresses, and this way we're going to partition. So partitioning doesn't need to be at the way level, it could be at the set level as well. There's actually lots of these kind of like works of showing that how you can do partitioning way-wise or set-wise or hybrid-wise. You can even partition at the software level or the hardware level or kind of some sort of hybrid method between software and hardware. And then there's also this CAT technology, cache allocation technology, I think, which Intel use. And this is actually a commercialized technology. And what it does is gives priority to different software. So for example, if your software is more important, it needs to have a decent performance, you can use CAT and say that, okay, I need to make sure that this particular software gets as much as cache as it needs, okay? So CAT is able to kind of like, provide these kind of dynamic use cases, especially for cloud applications. This is very important because cloud applications are competing for the cache spaces very regularly. So yeah, this is kind of like the idea of cache partitioning. If you're more interested to kind of go through the details of the actual kind of optimization algorithm and all, take a look at this paper. Okay? Questions? Yeah.
Is this specifically for cache partitioning, the cat thing, or is it gonna be applied to like adding weight to like not replacing this cache thing?
So yeah, CAT is particularly for just the cache partitioning. So it ensures that that particular application is occupying enough cache and nobody can kind of keep them out. So they're not really competing with other applications.
So when you're repartitioning, are you flushing anything out or you just keep it there?
I think the way it works is you probably don't need, I mean, for security reasons, you may want, but usually for performance reasons, you don't. You just, the next time that something comes, you don't let it to replace, right? So I think that's the least amount of overheads. All right, so that's it for cache. All right. So moving on. All right, so this is kind of like the end of our discussion for kind of these advanced topics in microarchitecture. What will happen from now on in this course is that today I'm going to mainly talk about this, side channels and kind of the security issues. Next 2 weeks, we're going to have paper presentations. Then on the third week, I'm going to again do two group of lectures, one about the main memory and issues in main memory, both security and advanced topics. And then I'm going to also talk about a little bit of memory safety and trusted execution environments. But kind of like so from now on, we're going to switch mostly now into the security aspects of the Mercury architecture. Now we have built all this knowledge about advanced topics. Let's actually dive into security. Any questions before we get started? All right. So, so today I want to talk about microarchitectural side channel attacks. Some of you have known a little bit about this. Some of you may not know anything about this. So let's actually talk about the details. And as I said, next 2 weeks, we're going to talk a lot about various different, newer papers. This is generally an area that's been very recently got lots of interest. Generally, cache side channels, the very first cache side channels has been kind of introduced in like 2013, 2014 timeframe. So it's like relatively new. This is like less than 10 years. And since then, there's been an explosion of these various different types of microarchitectural side channel attacks. There are a huge amount of interest in all of these companies to make sure that their designs are resilient against various different forms of side channels. And as you will see in the paper presentations the next 2 weeks, is there are many, many, many different types of these attacks. Today, what I want to show you is like the basics of a cache side channel attack, which is kind of like the main basic block in almost any of these attacks. And then we're going to talk about transient execution attacks, which is kind of like the big thing that kind of shows that, generally speculation is a very bad idea in terms of security. Okay. Of course, when you were talking about security, you have to understand why this is a big deal. And the reason for that is essentially we envision that we're going to see many, many more devices in the next few years, and we are even seeing it now. And then the second big thing is that not only do we see more devices, but we're going to see these devices controlling many more security critical applications. Okay, and then if you think about this and why kind of things like this digital side channels are a big problem, is if you think about the computing paradigm that we had in the past. In the past, most of the things was done locally. So you have one process, you were the only user of your computer. You kind of like, puts your application and task on the computer computes it, you get the results. Then the internet came out and things start getting connected to the internet and start sharing data. But nowadays, what we are seeing is that it's not just kind of like, oh, I have some message that I want to send you. It's complete sharing of anything, right? So you share your sensing, you share your actuation, you share your computation, you share your network. You even run your application in some cloud servers. You run your kind of your code and data and everything in like AWS or Azure or all of these kind of like different kind of cloud-based environments. Industries also do that. So essentially what we are now observing is that things are now remote. And when things are remote, there are two set of problems. One is I can't really barely trust the remote host because I cannot see it, I cannot kind of communicate with it regularly. So I can't trust my computer, but I'm not really trusting someone else's computer, right? That's one thing. The bigger problem is that let's say you can't find a legitimate remote user. For example, let's say we trust Microsoft. But the problem is that now Microsoft needs to kind of service to many, many different users. And it's now hard for Microsoft to authorize and authenticate and kind of vets the legitimacy of every single user. Okay, so everybody can kind of launch their applications on their marketplace and their cloud environments and whatever. If they make kind of limitations, they're going to lose money, right? So they don't want to also kind of say that, oh, you have to kind of come here and do the fingerprint and I don't know, like, show yourself and show your code. And so they want to make it as simple as possible so you can kind of just create an online account and then be able to use it. But on the other hand, it's actually make them vulnerable to any random user, any illegitimate user that can essentially offload any malicious task that they want on their system. So now we are kind of like in this hostile environment where things are remote and your applications may be physically co-located with some malicious applications, okay? And now under this regime, we need to secure our systems, okay? So what used to be just local applications are kind of, okay, now I know what is being run in the system, I can control things, but you cannot do that anymore. So we need to now secure the systems. So essentially what happens as a result of this is that there's just significantly more opportunity. That's kind of the birth of all these different side channel attacks, okay? So what is a side channel? Most of you know this by already, but generally side channels refer to just generally any signal, and that is created as a result of computation, okay? power consumption, sound, time, temperature, electromagnetics, so on and so forth, all are side channels. The big deal about side channels is essentially if it can measure some signals from the device, I might be able to understand something about the device. I can find the particular data that's being executed or the code that is being run. So essentially going back to the things that I said before, that if a malicious application can be physically co-located with a non-malicious application, if the malicious application can infer these side channel signals, then essentially they kind of have as if they have access to the other device, to the other application. They can extract, important information from the device, and that's the big deal. That's the worry that we have about side channels. There are two groups of side channels, analog and digital. The analog ones are physical signals as created by the device. The digital ones are the ones that we are interested in this class, and we're going to talk about it today. And these are the signals that are not real physical signals. These are actually because of the microarchitecture we can collect this. So for example, cache misses is something that an adversary can measure. And we're going to show you how by just measuring the cache miss pattern and cache hit pattern, an adversary can understand what the other user is doing. So that's kind of like the big deal here. And again, the reason that this is possible nowadays is that you can co-locate two different applications on the same machine. That's the big deal. So how do we enforce security in computers today? So this is the question that under these assumptions, how do we even kind of try to fix this? We fix this using three kind of main principles. The first one is what we call principle of least privilege, which means that you usually have kind of two layers when we are running things. We have the privilege layer and we have the user level. There are things that user level cannot do. And when we are running things remotely on these remote computers, one thing that we really want to make sure is that the remote user does not have privileged access. If they do, then they can do many, many things. So most of these scenarios that we're talking about are under this assumption that the remote user does not have privileged access to our system. If they do, then the game is kind of over, okay? So under this system that the user does not have access to the privilege, then we need to make sure that the system is secure, okay? And yeah, usually we call this user and root. There might be actually multiple layers, so it's not necessarily user and root. There could be user, root, and machine. There could be many other things. That's number one. The second thing that's very, very important is the principle of isolation. In most of the systems, in almost all the systems, we have proper isolations between applications, okay? So even if there is a malicious application and there's a legitimate application, if the malicious applications try to kind of access any data in the legitimate application, the operating system or the hardware will block this because there is essential kind of isolations between these different hardware. So a malicious application cannot read the values, the memory values of the other applications, cannot obviously write anything to them. They can only access to their own data. They cannot access to anybody else's data. That's the big part of any sort of secure system, having an isolation. And lastly, we have what we call a trusted computing base. The idea here is that we kind of like, in order to make sure that these two other principles are running properly, we trust on something in hardware, and we call that TCB or trusted computing base. The idea is that essentially the TCB is the one kind of you trust that, and you have a method to kind of build the trust on top of that. Okay. So does this work? Unfortunately, side channels attacks, sophisticated side channel attacks can break these assumptions, especially the assumption about the isolation, okay? So the isolation basically isolates direct accesses. Like, if one application tries to access the other application, this is kind of like blocked. But if the kind of malicious application try to use some form of side channel information, something that does not directly access this, but kind of like use some channel, including like, cache side channel and all, in order to infer some information about this, then there's no way of isolating this, okay? The only way to isolate this is to physically isolate. So if I use two different caches, then I'm good to go. But physically isolating is usually very, very expensive because you want to share the cache, as you remember I told you last time, okay? So essentially this is the idea of what we call the digital side channels, which essentially what it does is breaking the isolation assumptions on the system, okay? So how do we do that? Essentially, digital side channels is all about contention, okay? So what it does is trying to see the contention that it causes. And essentially the idea is that if the other application, the victim application is active or not active, the contention pattern will change. And as a result of that change in the contention pattern, the adversary can kind of, extract some information, okay? So if it's busy, it means that it's doing, for example, X. If it's not busy, then it means that it's doing Y, okay? So let me give you a concrete example using cache side channels, okay? So if you remember, I told you that we have this multi-core systems, and in multi-core systems, we need to share the cache, because if we don't share the cache, then our utilization would be horrible, right? So we share the cache among multiple users. And as I told you, now since we are doing this remote kind of cloud computing, these users could be any user, okay? So it could be just a victim, a innocent user who wants to really do its own job and compute its own systems. But unfortunately, we can also have a malicious user, okay? So the goal of the malicious user is kind of figuring out what this victim does, okay? So let's see how we can do this using a shared cache. So first of all, so the cache, for example, let's say in this case, I'm showing you a 4-way set associative. So these are sets and these are ways, okay? The first thing that would happen is that, first of all, if this victim tries to kind of access this line and puts their data in this line, if this adversary tries to read this line, it cannot. It will be blocked. Why? Because it's the same isolation principle that I described to you, okay? So just the fact that things are in the cache doesn't mean that the adversary can directly read them. They cannot read them because reading the memory and cache is blocked if you don't own it, okay? So this part is not doable, okay? The adversary cannot just directly read the victim's values, okay? So this we have, and this works perfectly fine. We don't have any issue. But what adversary can do is a little bit more sophisticated than this, okay? Let's see how. So let's say that we have this data-dependent activity that, based on the data, let's say the value secret, that could be either 0 or 1, okay? I'm actually going to show you a real code. But for now, let's say that the secret could be either 0 or it could be 1, okay? Now let's say that if secret is 1, we're going to access the cache. And again, I'm going to show you a code example that exactly happens like this. And if the secrets, the P or S is 0, we don't access the cache, okay? This is a simple problem like this, that the victim, based on some value, they may or may not decide to access the cache, okay? So let's see what happens. So we're going to have two possibilities, okay? The first possibility is that the victim is going to access the cache. So they're going to load some value. We don't know what value that is, but we just know that there will be some value by the victim that's going to be put in the cache, okay? So what the adversary can do is that, of course, as I said, we cannot first read this directly. So this is out of question. But what we can do instead is we're going to use this attack called prime and probe. Okay, so how does prime and probe works? The attacker is going to say you're going to do this 3-step approach. The first step in this prime and probe attack is that the adversary is going to first fill that particular set with their own data. Okay, so some random data, don't care. it just, the important thing about that data is that they have to be mapped into that particular set, okay? So all of them have to be mapped here. If this is a 4-way set associative, I need to find 4 addresses as an adversary that they all map into the one set, okay? So this is what we call an eviction set, okay? So we put this, and as a result, since I'm accessing this 4 ways, then I'm gonna evict everything else but my own data, okay? This is the phase that we call the prime phase, okay? So what happens now is that the adversary ensures that the only data that is available in the cache is their own data, okay? So now what happens? Now we are going to this wait period, okay? And in this wait period, 2 things can happen, okay? Either the victim gonna access this cache or not access this cache. 2 possibilities. If the victim accesses this cache, and remember, accessing means that P was equal to 1, then it needs to go through this set and it needs to evict one of these 4, depending on the replacement policy, it could be LRU or DIB or whatever. But whatever happens, one of these 4 should be gone and should be replaced by the victim data, okay? So for example, let's say this one is gone and then we're gonna replace this. And then here now we assume that P was equal to 1, okay? So we're gonna replace this number and put it into the cache, okay? Alternatively, it could have been that, you know, P was equal to 0, so the the victim doesn't access the cache and we move on, okay? So this is the end of the wait period. Now what we're gonna have is the probe period, okay? Now the adversary check again the cache and it's going to observe 2 possibilities. So essentially, so let's say this was address A1, A2, A3, and this used to be A4, okay? So the adversary gonna access A1, A2, all the way to A4, and it's gonna observe 2 possibilities. Either you're gonna see that all of them are a hit, or it's going to see that 3 of them are hits and 1 of them is a miss. How do we, how do we extract values from this? If this all were hit, it means that the victim didn't access the cache. In other words, P was equal to 0. If 3 of them were a hit and 1 of them was a miss, it means that the victim accessed the cache. In other words, P was equal to 1, okay? And then the beauty of this is that at any given point in this kind of prime and probe application, all the adversary does is just accessing A1 to A4. It never tries to directly read the value of the memory or tries to kind of block or change any of these isolations. Anything that the adversary does, completely, legitimate in terms of, the rules that we set in our systems. We just access A1 to A4 one time. This will result in insurance that all these 4 different values are loaded into the cache. Just we wait for some period, few hundreds of cycles, and then we access the same set of 4 different addresses, and then we just see whether we get a hit or we get a miss. How do we know that we get a hit or we get a miss? We're going to use this fact that cache hit is much faster than cache miss, okay? So we're going to use some form of a counter, and count how long does it take for this data to be read. If it's a short amount of time, it's a hit. If it's a long amount of time, it's a miss, okay? So essentially, we can just use an internal counter, very simple to do that. You just use a counter. And then you will see your hit or miss pattern. If you see all hits versus 3 hits, 1 miss, then that's your answer, okay? Yes.
Adversary is trying to get the value of P.
Get the value of P.
So why does it come? They can get it from 4 hit and 3 hit per miss also.
Yeah, so the question is, how do you know you have a miss?
By scan.
So think about it, like you're writing a code, like a C code, okay? So what you're gonna do is that you're gonna do A1 to A4. How in your C code you know this was in the cache or not in the cache?
But we know what we wrote in the time, right? So we can check whether A1 is that or A2 is that, A3 is that.
It's always that. It just takes more time to get it. So when you're doing A1, for example, like in your regular code, right? When you say A1, you're gonna get A1. You're not gonna get whatever was in the cache. You're always going to get A1. You might get A1 quickly because it was in the cache, or you might get A1 after a while because it was in the DRAM. It was not in the cache. As a programmer, this is not visible to you, right? So when you're running your application, you will not see the difference between the data that's coming from the cache versus the data that's coming from the memory. Does that make sense?
No, but we were writing to the cache, right? We were writing the data, so we could fix the value of A1 there and then compare that value rather than comparing.
No, again, you're kind of missing the point. So you have a function. Think about it at high level, okay? You write a function, you have for I 0 to 3 and A1 AI, okay? And then I don't know, like you write this AI to some Y, okay? So you're suggesting that I'm gonna check Y and see what is the value of Y.
I'm suggesting that once we do this cache, that time we check the value of AI with respect to Y. If AI is the same.
It's always the same. That's my point. So you're not gonna get different values of AI because there's different content in the cache. You're right because you never like if you don't have access to that line, you're not gonna get it from the cache. You're gonna get it from the memory. You're always gonna get same AIs. It's just this might take 30 cycles or it might take 100 cycle. That's that part you don't know. Yeah.
This has like a lot of assumptions on like. You know which row the cache is being written to, you know exactly that this program writes to this given this behavior. Is there like a technique to find that stuff out?
Yep.
Okay.
That's what you're gonna see next week when people are gonna present those papers. So there's all about these engineerings. These are all engineering, right? How do I find what we call the eviction set? How do I even know which set the victim is gonna access, right? Because that's the first question. Because
Right.
P1 or P2 gonna land into one specific set. So the first thing is I need to even know what that set is. The second is I need to create an eviction set that actually maps directly into that set. The third is how much should I wait? Should I wait 100 cycles? Should I wait 1,000 cycles? Should I wait 3,000 cycles? How much should I wait? And then the last thing is how do I count between my misses and hits? Like, for example, what if it's L1 miss, but L2 hit? What if it's L1 miss and L2 hit and L2 miss? What if, for example, we have a prefetcher? What if we have a different replacement policies? All those tricks in real systems, the adversary has to kind of like, tackle that, and then tons of papers and all of each one of those. We're going to see a little bit of more details on things.
That's just not when we talked about shared cache. We said that we assign a fixed portion of the cache to each process. So how come they can?
No, we're not assigned. So first of all, that was just a partitioning, but that was also dynamic, right? So we never assign a fixed portion to anything. We let them to fight. You can do utility, but again, utility also changes over time. Okay, so there's no notion of fixing things because if you fix things, then you no longer have a shared cache. You want to have a shared cache because you want to utilize the space.
But they can write to the same like set. I thought the sets would be like split.
No, so even the utility one was, as I said, the ways are partitioned. Okay, but again, they are dynamically partitioned. They're not statically partitioned. Okay, you can also do set coloring. If you do set coloring, then yeah, so you can only write into one particular set. This is actually one of the ways that you can eliminate this, but these are usually not very helpful because it significantly reduce your performance. So nobody likes any sort of kind of, because the ultimate solution is making everything private, right? If you make everything private, then you're good to go. This never happens. But private cache is not great.
Why do you need a full set? Like, why can't you just have a random place in memory, write your data to it, and then read back later and see that there's a delay? Like, why do you need the whole set?
Because then how do you know that the victim, so let's do the alternative. So let's say we have 4, and then the adversary fills 1 instead of all 4, okay? So now what happens? The adversary waits. Now the victim comes and the victim wants to kick something out. How do you know he's going to kick this out? Maybe this kicks this one out. So in that case, that's the third time the probing comes, the adversary is going to see that, oh, my data is still in there. So, oh, that means that the victim didn't access the cache, but it did, in fact, right? So you want to ensure that you feel such that if the victim wants to evict, it is guaranteed they're going to evict your data. Otherwise, it won't work.
So the assumption is that you know that the victim's going to write to this cache line, refill the cache.
Yeah, either gonna be or not gonna be. Either one gives you one bit of information. Okay.
How will you ensure that you are reading from the same cache line?
You know the addresses, right? So on the attacker side, you do A1 to A4, and then you wait, and then you do again A1 to A4. So this means that they all land into the same address, right? Same exact address over and over. Yeah.
How do we make sure that there are only two users using the same shared?
Good question. So it could be also the third user also kick this out, and that could be noise to your system. Usually you can repeat this process multiple times, and then hopefully you will see it on average behavior. Yes, but it could be like, it could be 4 cores, and then there could be a third core also using the same line. In that case, that might change.
When the attacker is checking the cache again for the access pattern, it will replace the data again.
Mm-hmm.
So will that not cause a problem to the normal execution of the program?
No, because it would be a cache miss, so it's just a performance, right?
Add to the latency.
Add to the latency, right? So you just, not only you're stealing the data, you're also, forcing that system to be performed poorly. So the victim gonna see that things are slower, but that's it. That's the only thing that the victim will know. But slower could mean anything. Could be another legitimate application also causing slow down. Right? All right, so as I said, this is what we call prime and probe. How realistic is this? This is actually run on real code. So those of you familiar with RSA, this is the snippet from part of the RSA algorithm. The big thing here is this line of code here, that based on 1 bit of the secret key, we're gonna do either the multiplication or just the modulo operation, okay? So if EI is equal to 1, we're gonna do multiply and then modulo, okay? If EI is not equal to 1, then we're gonna skip this and just do the module, okay? So we're gonna do, usually call this multiply and square or just square. And then what we're gonna see is that if we see the 2 together, okay, so this is actually from a real data. And as you can see, this will result in a different access pattern because this will result in an additional memory access, okay? And then if I time it, I'll see a pattern like this, which as you can see, you will see that, some of it are like this, some of it are like this. There's like this kind of behavior, some of it is just this behavior, okay? And you can see that this means that this bit is equal to 1. This means that this bit equal to 0. Bit 1, bit 1, bit 0, bit 0. Okay, so it's kind of like this. So this would be 1, 1, 0, 1, 1, 0, 0, and so on and so forth. So you actually can see the exact pattern based on this pattern that you're seeing here. Okay, and this is from a real system. As you can see, it's not exactly the same all the time. It's a little bit noisy, but if you do it in proper times, you will see that you can actually get the average behavior of the system. Okay. Another thing that people have shown is that you can actually even do this to extract some other information. So for example, think about matrix multiplication, okay? So matrix multiplication brings some data from the cache and then multiply these two together, okay? So now I can, based on seeing this access pattern, I can see how big was your matrices, right? how many times you have multiply, and all those things. In other words, I can basically know the structure of your network. And why would that be an important thing? Think about ChatGPT. If I can somehow get my hands into ChatGPT model when it was running, now we'll know the exact structure of ChatGPT, and that that worth millions of dollars these days, right? So if I know exactly what is the exact connections between different layers of something like ChatGPT, then I can go and build my own ChatGPT, and I can have a very $1 million worth company. Of course, I still need the data, but the structure itself is important, right? So if someone can essentially steal my model or extract my model, then they can go and replicate my model and do whatever they want with it, all right? So things like that could also happen with a cache side channel attack, all right? There are tons of other variants of cache side channels. There's flush and reload, and flush and takeaway, and streamlines. Some of it we're gonna discuss next week. Some of your students, your classmates, gonna present these papers. But essentially, most of them are based on this fundamental logic of there is this kind of multiple phase approach that you, based on the access pattern of the victim application, the attacker knows something about the data. Okay. For example, I'm showing you another one called flush and reload. The flush and reload is a little bit simpler than prime and probe. Here we assume that the victim and the attacker share a line together. The reason that different applications might share a line is because, for example, think about all these standard libraries like printf, scanf. These are all codes that are actually like lines in the memory. Okay, so instead of like copying all of these to every single application in order to save space, the operating system just share it. Okay, so if the attacker shares some particular line with the adversary, so with the victim, all they can do is basically the attacker can do this. The attacker flush that line, can force that line to be flushed. Okay, there's a particular instruction in x86 called CF flush that can do this. So it flushes to the DRAM. The victim gonna access, the attacker gonna measure. Two possibilities. Either the victim access the same line, which means that now it will be a hit, or the victim didn't access that line, then that would be a miss, right? And again, same story as prime and probe. If the data was 1, we access it. If the data was 0, we didn't access it. So again, by just measuring the hit or miss of this shared line, I know whether or not the adversary access it, and whether or not the value that caused this access was 0 or was 1. Okay. Is the cache's only shared content for this? No, there are actually tons of papers that shows branch predictor has the same issue, TLB has the same issue, DRAM has the same issue. Any sort of things that can cause contention could potentially be exploited the same way. And again, as I said, we will seeing an explosion of these number of different shared units in our systems, unfortunately. Okay. Here's a tons of different examples: GPUs, DRAM addressing, directional branch predictor has been attacked, TLBs has been attacked, and so on and so forth. Let's have a quick break and then talk about how do we defend against these attacks. All right. So how do we defend against cache side channels? Well, give me ideas. Yeah.
Anytime that you're going to access a set of memory, access it anyway, even if you're not going to use it,
Okay. What's the trade-off for that?
waste operation and waste.
Mhm.
Yes, so
Okay.
hash your, the reason why this happens is because you have your memory address will always map to the same point in the cache, but if you hash it with some other value, then it won't always get to the same point in the cache.
But then you need to know where it is, right? And so you kind of randomize your address.
No, you have a bit that says like what. You can hash that with that bit and then
Uh-huh.
kind of move itself within your cache.
Okay.
And You just have to store an extra bit.
Okay. But then the adversary might also be able to see that, right? Like you need to it's a kind of cat and mouse problem, like who can know it faster. But it's kind of you move and the adversary needs to follow you. If they
Yeah.
can find it, then you're good. But no, yeah. What else? Yeah, that's actually I think the Caesar's paper. That somebody gonna present. What else? Yeah.
Don't write it back to the place where they.
What should we do? Don't use cash. What else? Yeah,
We have a victim character so that the access time. of the user-
but eventually you're gonna see the access time, right? Like, you're gonna have misses, whatever you do. Any other suggestions?
Is it possible to map both of the different operations that you do to the same cache line?
Well, it's more of like accessing or not accessing. It's not more of like accessing to this address versus that address, right?
But like in the case of RSA, you're doing the multiplication or not, so what if you just map the modulus operation to the six, well,
It's the same thing you said, right? Like always access the cache. Right?
Yeah.
Which is the good answer, actually. Anyone one last time? Any final suggestions? Okay, let's see. So first of all, you can do what we call oblivious or constant time programs, as in don't do things that are kind of like if you do this, you access the cache. If you do that, you don't. Okay. If I always, regardless of what I do, I have the same constant time, there is nothing to observe. Okay. So if I do this, I access the cache. And if I do that, I also access the cache, then the adversary learns nothing. Okay. This is what we call oblivious programming or constant time programming. Essentially, you don't create any timing channel in your code. Okay. This is very hard to achieve because you need to, have a good model of the timing model of your system. Plus, you need to essentially add this in every single place. Means that your code size will grow, your power consumption will grow, your performance will drop, and all those things. But it works very well because essentially you kind of cut it from the source. You never actually leak any information. Okay, that's great. And then this, by the way, can be done either at the software level or it could be at the compiler level. So the compiler can also observe this timing behavior and change it, or the software developer themselves can see this timing behavior and change it. Any other question?
So the time would be constant to whatever the memory access time is.
Would be yes, or if you don't access the memory. Essentially, the idea is that don't do this or that. In both cases, do the exact same thing. Either accessing the DRAM, accessing the L1 cache, whatever it is.
Then it defeats the purpose of using a cache.
It doesn't. It doesn't. It's at some points it does. At some point it doesn't. Yeah, but yeah, you get performance loss. Essentially, you're limited by your worst case performance. But you might get cached in both cases, right? So it doesn't completely defeat the purpose. So what I'm suggesting is that instead of having if A access the memory, else don't do anything, do this. If A access the cache, else access the cache. Okay. But just here, you need to access the dummy data. This is access dummy. This is access regular data. Okay. No, that's dummy, right? So you bring something that you don't care, you just ignore it. You save some random register and that's it. Right? As long as the correctness of your application is not changed, then you're good to go. Does that make sense? I'm just adding dummy instructions to my code.
But if that data is not in the cache, then we need to bring it from the main entity.
We need to bring it from the main memory.
That
So you
can-
have to also be careful about the cache access pattern. So if this is a hit, you have to make sure that this also is a hit. Right? So it's a little bit tough, but you can do it. Any other question? Okay. So this is what we call constant dynamic programming. This is the gold standard for any sort of side channel detection. The second thing that we can do is kind of like along the lines you said, partition the cache. Okay, if the cache is private or it's partitioned, then we are good to go, right? There's no contention because they're physically separate from each other. Okay, the downside of this is that you lose utilization of your cache and ultimately you will lose performance. The third one is let's actually randomize it. Okay. So what we can do is that we can add noise to these measurements, okay? We move things around, we change the delays, the hit does not take the same amount as before. So the adversary doesn't really learn anything from measuring anything because everything is randomized in terms of noises, okay? Another thing is monitoring, observing that this thing is happening and then doing something about it. If I see that somebody is doing prime and probe type behavior, I can detect it and I can do something about it. Okay. For example, there are papers that shows that you can detect these kind of patterns because we are great at detecting patterns, right? We are great at detecting branch prediction patterns and cache replacement patterns. We can also detect attack patterns. Okay. So if I can detect the patterns, then I can do something about it. All right. There are a whole bunch of others as well. We're gonna actually see some more papers. I think on Wednesday next week when we were talking about defenses. I think on Monday we're gonna mainly talk about attacks. On Wednesday we're gonna see the defenses. So there you're gonna see a little bit of more detail. Questions? Good. All right. Generally, the challenges in all of these defenses are threefold. There's the overhead that comes with all of these defenses, essentially the performance and area, the accuracy of the detection or prevention, and the feasibility of the approach, right? So whether or not this is possible to do that. In some cases, it may not be possible. So when we're listening to the papers next week, pay attention to these differences and you will see that, how each one kind of fare against the others. All right. Another thing I want to talk about cache side channel is what we call covert channel. So the covert channel is intentional communication between parties. So side channels was unintentional. There was like a victim and the information from the victim was extracted by the adversary. The covert is between two adversaries that they talk to each other, okay? So they use, for example, a cache side channel to talk to each other. Why they want to talk to each other? Because they don't want to use regular channels. Because if they use regular channels, they will be detected or they will be blocked, okay? But if they use covert channels, then nobody understands that they're actually talking to each other. So they can continue talking to each other, okay? So why do we need this? Essentially, we need this to break the least privilege principle, okay? So for example, let's say that we have an application that has access to some database. Let's say my photos in my machine, okay? But since this is like a least privilege, it only has access to that database, but doesn't have access to the camera, doesn't have access to the microphone, doesn't have access to the Wi-Fi and all those other things, okay? But now let's say there's another app that has access to the Wi-Fi, but obviously doesn't have access to the libraries and photos and cameras and all, okay? So now if an adversary can kind of like run these two applications, one that has access to the photos and the other one that has access to the Wi-Fi, what they can do is that if they can form a covert channel between these two apps, the data can be extracted from the photo library, sent to the Wi-Fi one, and then send out to the outside world, okay? This way we kind of circumventing this protection layer in the operating system. If the one that has access to the photo library tries to connect to the Wi-Fi, it will be blocked, okay? If the one that has access to the Wi-Fi try to access the photo library, it will also be blocked. But if they can communicate covertly, then they won't be blocked, okay? So this is the whole point of a covert channel. And how do we do covert channel inside in cache side channels? Anyone who wants to give me a simple algorithm between, let's say, there's A1 and A2, and let's say they know a set. How do we create a covert channel between, how do we communicate between these two? Anybody wants to suggest? Using prime and probe, for example, there's a simple prime and probe that we can do in order to send data. Yeah.
It's a one, it's a miss, it's a zero, it's a hit.
Yep, exactly. So we do Morse code base, right? So A, for example, let's say A is the transmitter and A1 is the transmitter, A2 is the receiver, okay? They're gonna agree on this fact that if so receiver A2 gonna fill the cache first. So this is gonna be done by this. Then they're gonna agree on this fact that if A1 access is sending bit 1. If it didn't access, it sends 0, okay? So A2 gonna prime the cache, gonna wait for some time for A1 to transmit, and then you're gonna probe, okay? During the probe, we're gonna see two things, right? Either gonna see the same data, all 4 hits, or it's going to see that there is 3 hits and 1 miss, which means that there was 1. So each time that we do prime and probe, we get 1 bit out of the system, and then I can send infinite amount of bits using this, right? So they only need to synchronize 1 time, and then boom, 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 they send data, they extract this data that they want. If it's like, I don't know, like, 1 megabytes of data, it's just depending on what's the bit rate of this, like how long does it take for sending 1 bit, then we know how long we need to repeat this process in order to have a cache system, a covert channel system. Yeah.
Assuming that no other process is accessing your cache line, couldn't you send an entire set of bits at a time?
Yes, you can, and that's your project, right? So your final project is a covert channel championship, which we're going to ask you that whether you can build a real covert channel, and the one that can build the fastest would be the winner, okay? And then you're welcome to do all these tricks that send more than 1 bit, sending faster. You can use more sophisticated communication protocols. So this is what we call on-off keying, OOK, okay? This is like basically simplest communication protocol that we have. But we have many other protocols. We have FSK, frequency shift keying. We have PSK, phase shift keying. We have QAM, and so all these communication strategies that we have in like commercial systems, your LTE device, for example, you can use all of those kind of communication strategies in order to send. The trade-offs, of course, is it gets more complicated. You need to implement it, and so on and so forth. So that's really the challenge. Does that make sense? So yes, you can do all those things, and again, there are tons of papers talking about how do we make, this covert channel faster, how we make it less noisy, and all those things. Cool. So kind of the key takeaways here is that shared resources leak secrets. It's possible to extract secrets using digital side channels. And we need to find the balance between security and performance. You don't want to completely eliminate caches just because they're leaking, because we did all those tricks that we discussed in the past few weeks to improve performance. And now we learn that, look, those tricks is actually leaking secrets. So now we kind of need to take a step back and thinking about defenses. The problem, though, was when we were designing those things, we had no idea that these things existed, okay? And now we are kind of like fixing things rather than really designing things, okay? And that's the status quo of microarchitectural security. That we have all these features. It's exactly the same way that we teach this class, that we design all those features, and now we are left with this bunch of features that are all leaking information, and now we're kind of like say, okay, what should we do? Right? This is the problem that we're facing today. Okay. Let me give you another big example of digital side channels attacks, and this is what we call transient execution attacks. This one is actually a very big deal when it was introduced back in 2018, 2019. The main two ones is Spectre and Meltdown. So today I'm going to talk briefly about those, if you have time, obviously. So remember that we had out of order execution, right? We had in order front end that we fetch and decode in order, but we were executing things out of order, right? And then how did we fix the exception and miscalculation? We fixed it using the ROB, right? So we kind of like commit in order and we flush things out if things get wrong, right? And it works. It works very, very good, and it gives us a lot of performance. And we talked about tons of different features to improve this, right? So let's see actually what happens with this transient execution attack. So the idea is very simple, okay? The idea is that we can create this transient windows. What are the transient windows? The transient windows are those windows that the speculation happens. Think about a branch, right? So a branch comes, we don't know the outcome. So instead of waiting, what we do, we start speculating, right? So we assume that, for example, the branch is taken. We start executing things, okay? The time that we start executing things speculatively, we call this a transient window because we're not sure whether these instructions are going to be really committed or whether we need to flush them, okay? So we're going to let them go, but then if we see that we made a mistake, we're going to flush them. If we see that we didn't make a mistake, that's great. We can just keep them in our pipeline, okay? So now the idea of these transient execution attacks is this, that during this transient window, do something illegal, okay? Do something that you normally couldn't do. For example, access a particular address in the memory that if you did it in a real system, you would have got an exception, okay? When you do it in the transient window, you're not going to be caught because you're in the transient window. The CPU is not going to handle the exceptions because there are other exceptions before you, because we are in the speculation window. So until we don't know even the outcome of the branch is taken or not taken, I'm not going to take care of, like, younger exceptions. So I'm going to let things go, okay? And as I let things go, the adversary can do these illegal activities. It can read things and bring things and so on and so forth. Eventually, that transient will be resolved. Either it's going to be kind of like true or not true. If it's not true, which means that if things going to be flushed, then I can safely ignore that exception. Or I can even take that exception, I can capture it, and I can do something about it. But by the time I already finished my illegal activity, in other words, I've read what I'm supposed to read, or I did what I'm supposed to do, okay? And the big thing about this is that especially for reading memory, during that illegal time, I can essentially read arbitrary values from the memory. Although I can never read the exact values, but those values will be brought into the cache, okay? Because remember that we had load speculation, right? We didn't know the address, but we just assumed that there is no problem. We issue the load because of the LSQs that we had last time. So as a result, the data will be brought into the cache. Even if we kind of flush things out, we're not going to flush things out of the cache, okay? So the illegal data that we brought is going to be stored in the cache. Now, all I need to do is a cache side channel attack to actually read that value, okay? So now it's kind of a two-step algorithm. The first is I do something illegal during the transient window. I force the system to bring that illegal value to the cache. And now I know what I should do. I will use a cache side channel attack to extract that value. So this is kind of like, kind of a cloak dagger kind of thing. So you do like a 1-2 punch kind of attacks. Okay. So what can we do with this? There are many, many things that you can do. You can read arbitrary memories. You can actually jump through various different parts and so on and so forth. And there are many, many different ways of doing this, okay? And again, this is another one of those, there are tons and tons of papers of doing different variants of this. So Spectre and Meltdown are the two first attacks that did this, but each one also had their own variants. But since then, so these two attacks kind of introduced 2018, 2019. Since then, there's kind of like many, many different other types of transient attacks. Like for example, load store queues has one, branch prediction has ones, exceptions has ones, data value injections has ones, prefetching has ones. So all of these, and then these are the papers some of it we're gonna see in 2 weeks, these different types of attacks. But let me actually first explain to you these two main ones, the Spectre and Meltdown. These are the big ones. First of all, as I said, the general idea is this, that during the transient window, we're going to access the secret and then transmit it into the cache. And then the attacker going to use some form of cache side channel or any sort of side channel attacks to actually extract it and bring it to their own domain. So the data that's supposed to stay within the victim domain, now using the side channel attacks, is now in the attacker's domain. That's how we can read this arbitrary values. Okay, so the examples, like let me give you a simple example. Let's say you have a sequence of code like this, that we have, like, let's say the kernel address that basically reads some secret. And then let's say we have some sort of activity based on that secret. So the secret is the index of some other array, okay? So if you can think about this, this would result in two loads. One load for bringing that secret value, and the second is from using that secret value as the index to bringing the data from this probe array, okay? So two back-to-back load number one and load number two. This load number one is protected by isolation. If I, as an adversary process, if I don't have access to this address, I'm not supposed to read it, right? So this will result in core dumps or segmentation faults and all those things. This is the principle of isolation I told you about, okay? So in regular systems, if I run this, this will be blocked and everything is fine, okay? But now let's see how transient execution attacks can actually make this possible, okay? So now let's think about an out of order system that this particular instruction is not the head of the ROB. In other words, there are a bunch of instructions before this, okay? So essentially this will happen something like this, okay? Two possibilities, okay? So the first possibility is that load number one started being executed, okay? Load number one will be, and then load number two at some point might start, okay? If by the time that load number two is going to start, a load number one is already committed, we're going to see the exception, right? Remember that we were not supposed to read this. This would have resulted in an exception. So load number two will be flushed and we're not going to see it, okay? So nothing bad happens. But now think about this scenario, that load number one start being executed, okay? At some point it finishes the execution, but since we are still in the transient window, we're going to also issue load number two. And as we do issue load number two, then this will be issued in the memory and bring the data in the cache. At some point in the future, we're going to commit load number one, and we will see that this would have been an exception. So we're going to flush things out and assuming that, okay, things are okay. But as you can see, we have already issued load number two. So too late, okay? So even if we are kind of flush things out, but we already issued this, okay? In other words, the adversary will know the exact index of probe array because all they need to do is knowing which address this was. If I know which address this was, then I know the value of secret, okay? So that's all I need. And I can control this probe array. This is the array that adversary controls. It can basically just read the value in this probe array and know which one has been loaded into the cache. That's all I need to do, okay? So essentially, I'm translating the value of the secret into address of memory. And by doing cache side channel attacks, I will learn that address of the memory. And as a result, I know the value of the secret. Does that make sense? This is what we call a meltdown attack, because this will cause an exception. The exception should have been caught, but it's still caught, but it's too late when we caught it. Okay? When we catch it, the load is already issued. So if this was here, we were good, but since it's after this load has been accessed, it's too late. Okay? So yeah, these are the details. Attacker allocates the probe array, let's say with 256 K lines, flush all of them off the cache, make sure that none of them is actually already cached. Then the attacker executes, the code is shown here. Then what we will see is that which address has been loaded into the cache, that's this value of the secret. Okay, that's how we're gonna know the actual byte. Okay. The second option is, so the meltdowns kind of can be fixed if we actually catch the exceptions as fast as possible. So there are fixes for meltdown. The one that we cannot really fix is Spectre. Okay, very similar idea, slightly different way of executing this. So the difference here is that we are not doing exception, but we are doing branch prediction. So consider a scenario like this, that we have a branch based on some value. Okay, and let's say this value is not in the cache, is in the memory. So we have to wait for a long time for this value to come. Remember, now you're an expert in branch prediction. Let's say this branch prediction predict that this branch is taken. Okay, if it's taken, it means that I need to execute this and this. Okay, so what I'm going to do is that I'm going to boom, issue load 1 and load 2. Okay. Issue load 1 and load 2 allows me to read arbitrary values for load 1 and load 2. And it takes some time for the branch to be resolved. At some point, the branch will be resolved. And we say that, oh, okay, those instructions, just flush them, right? And we continue, right? No exception supposed to happen. We just fetch some incorrect instructions and we're going to flush them. No, nothing bad supposed to be happen, but the same story as before. Because load 1 and load 2 was already issued, their data is in the cache. And again, if I can do the same address checking, I can know exactly the value of the secret. So I read X, and this X could be any arbitrary value, right? I can read whatever I want from the entire memory space. All I need to know is now knowing the address of that array. That's all I need to do in order to do the cache side channel. Okay? Questions? Yeah.
So is the point that the value stays in the cache even after the instructions flushed? So
Yes.
you can go find it later.
Yes, because you cannot, when you're flushing, you're not flushing it from cache, because you don't know what you have stored in the cache, right? If you know what you had stored in the cache, you need another cache for remembering what you have stored in the cache, which is not feasible. So when you store things in the cache, you just forget. All right. There are a bunch of variants for Spectre. This is variant 1. Variant 2 could be the target. Okay. So for example, I can force the system to jump to any other arbitrary value. So here I assume that the branch is taken, right? But what if, for example, I assume that the branch is taken, but also poison the target, so it jumps to somewhere I want, okay? And then that's where I'm going to run this, okay? So I can not only kind of predict that it's taken, but I can also change the branch target to whatever I want. And there I can then run this kind of what we call a gadget. This is a Spectre gadget, okay? So, and then how do I poison my branch predictor? I just run it with bunch of different, like, we know how to, predict, train a branch predictor, right? So we just run it with a bunch of different predictors, with a bunch of different targets, and boom, we have a branch predictor trained. Because all the branch predictors works in history. So if you give them wrong history, it will learn wrong history. So it will jump into whatever you want them to jump. Okay. So this is what we call variant 2 of the Spectre. It's just the exact same mechanics. The difference is the address that this jumps to is different than what address is supposed to. Okay. So how do we fix this? Anyone wants to give me suggestions? Stupid idea, welcome. Naive ideas also welcome. Yeah,
Caches should be flushed after when knowing that it's.
cat should be flushed after misprediction.
Yeah.
Sure. Horrible performance, but sure.
But no, not after misprediction, but knowing after that the instruction was the faulty instruction, they were not supposed to accept that.
Yes, so you remember what you have cached and then flush that at least.
Yes.
Yes. Good. What else? Yeah,
Could you somehow augment the address that it's being read into and only read like one certain process's memory into cache that is assigned to that process, like the partition scheme?
so not allowing others to read particular addresses?
Well, like. The problem is you're reading address or memory into a cache and then you can read it later, but if you partition the cache and say that this process can't read it.
Well, this code is running on the adversary's process, not on the victim process. So this is adversary. So we are in the adversary domain. Even if you partition, you're loading in this into the partition of the adversary, not the partition of the victim. So partitioning won't help.
Okay.
Other suggestions? Like there's a very simple suggestion.
Maybe to avoid issue to the most instructions.
Yeah, avoid speculation, right? Like disable the speculation and you're good to go, right? Like don't issue loads if you're not sure. Wait until things get committed and then issue loads. Then you're good to go, right? This never happens. Any other suggestions? One last one. So we're gonna see it more next week on Wednesday. We're gonna talk about the defenses, okay? So there are plenty more. So of course, the first one is disable speculation. Maybe not always, but there are actually solutions that kind of temporarily disable a speculation, okay? There are these fences that you can put, and when you put fence in your code, this actually, temporarily disable speculation. Okay. You can also protect your branch predictor, for example, from being mispredicted or being poisoned. Okay. And then the last thing is kind of like you were trying to touch upon it, that you can make your speculation invisible. In other words, if you're doing things in the speculation window, maybe do it, but maybe store it in some form of a buffer. And if you made a mistake, then kind of, invalidate that buffer. Okay. So this way we what we call like an invisible speculation or invisible, So this is one thing we could do as well. You're going to see a bunch of like real solutions next week, actually in 2 weeks, when we were talking about the defenses of speculations. But this is a very big deal because, all of our modern processors are actually, vulnerable to this attack. All right, so final takeaways from today's speculation fundamentally could be exploited because it bypassed some checks that we had for isolation. It can be then combined with regular side channel attacks like a cache side channel attack to bring the data to the channel that we want. Mostly it's cache, but it could be other things. So essentially the attacker forced the victim to bring the data to the place that they want. Then they launch their kind of deadly side channel attack. And that's where we're gonna actually read the value. Defense against them is very, very challenging because most of them are basically the fundamental step in speculation. And if you want to protect it, you basically have to get rid of all these nice features that we had in our system, which means that we don't want to do this, or it's not even feasible to do this. Okay? So next 2 weeks, we're going to see a lot of these real papers for attacks and defenses. Yeah, that's it, guys. See you next week.